So today we are actually here live to you know to discuss a very important topic of supply chain, which is spend analytics. Spend analytics is something every supply chain professional or every company wants to try and create spend management solutions. So we will be discussing about spend management solutions today, and one of and we'll be using spend analytics as a tool to create the spend management solution. The entire structure of the session will be like we will be discussing about the data, what kind of data we require for spend analytics, what is the algorithm we are going to use for spend analytics, what is the output we are going to get from the spend analytics, how we are going to use that output to derive the spend management solution. So this is what we are going to discuss in this pretty small session. Uh, and we're going to use the algorithm, which is logistic regression. Logistic regression is a algorithm which is a machine learning algorithm, but we are not going to use Python or R to actually to use logistic regression. We're going to use an Excel solution or Excel platform to actually come up with this particular or to use the logistic regression on the data, right? So without wasting time, I would move into the data now. So I will share my screen. So guys, before moving to the spend management or spend analytic solution, I would like to define how we are going to approach this entire spend analytics solution. So we are going to use a cause and effect model. The cause and effect model is a model which actually helps us to reduce the noise and move towards the signal. So it's cause and effect solution or cause and effect model is the model where we are going to reduce the noise and actually move towards the signal. So we are going to suppose if we have hundreds of causes or 200 of causes, right? So all the 200 causes may not be responsible for the cost savings. So if we're talking about so what we need is that we need to define our we need to define our cause and we need to define our effect. And when we define our cause or effect, right, we also have to define the effect mathematically and causes also mathematically. So what is mathematically? Suppose if I say spend solution, if I want to manage my spend, so how do you define a spend? How would you manage a spend? Right. So if I discuss about the spend is all about how much we are spending, right? On suppose we talk about raw materials spend, we talk about the MRO spend, right? So if we talk about the MRO spend or the raw material spend, so what is the spend? How much we are spending on the MRO purchase? How much we are spending on the raw material purchase, right? That is one of the way we can define the spend. The other way we can define the spend is cost savings, right? So here we are going to work on the cause and effect model, and so we are talking about the cost savings. So cost savings is all about how much we are saving on the purchase. So if you're talking about the savings, it's not about the discounts. If you're talking about the savings, it's not about the discount. It's about the targets, what kind of targets we have set before the purchasing. So every company will provide you. Suppose you're working on an organization, and the organization will provide you targets. What are the targets you have to purchase a specific raw material or a specific amount? Suppose you have a raw material. Let's say suppose you have a phone manufacturer, right? And you have to purchase a camera. So you have a target to purchase. You have a target price to purchase the camera. So let's say the target price to purchase a camera is $200, and you purchase the camera in $180, right? So your savings is $20. So this is what the purchase price variance. How much is the variance you have the target price? So that is a cost savings. How much savings you have generated from your target price? That is what we need to actually target. We need to fix, right? So that is cost savings. Now, if you talk about cost savings percentage, so let's say the purchase price, the target price is equal to $200, right? And your purchase price is $180. So what is the savings here? That is target price minus the purchase price, that is $20 US. Now, if I want to measure the cost savings percentage, that is the cost savings, so it's $20 divided by target price, right? So, and this is almost equal to 10%. So what we are going to define is our spend targets, or the cost or the target of the model is cost saving percentage. The target of the model is cost saving percentage. So this is our effect in the model, or this is our dependent variable. So we are not taking the purchase price as our spend as our target model, or the cost dependent variable, or the effect model. We're not taking even cost savings also the target of the model, or the effect or dependent variable. We're taking the cost saving percentage as a target of the model, or the effect of the model, or the dependent variable of the model, right? This is our dependent variable. Okay. So now what we're going to do is we're going to categorize. We are going to categorize this cost savings percentage. So if the cost savings is more than 15%, we'll define this 1, or else 0. Means if anything, any cost savings Let's say the cost savings more than equal to, I'll put more than and equal to 15%. And if the cost savings less than 15%, then we'll define it 0. So this is all categorical variable. We are converting our cost saving percentage into a categorical variable. We are converting our cost savings percentage as the categorical variable. So whatever say is the cost saving is more than 15%, more than and equal to and n equal to 15%, then we are defining this one. If the cost savings percentage is like the cost saving percentage. Now, the cost saving percent is more than and equal to 15%, then this one. The cost saving percentage is less than 15%, we'll define it as 0. Right? So this is our categorical. So we're converting our cost saving percentage into a categorical model, because we are going to work with a machine learning algorithm that is logistic regression, which needs the effect or a dependent variable in the form of category, binary category. So we are going to use the model with logistic regression to come up with our spend solutions, right? Using logistic regression. If I have to logistic regression, if I would have used another machine learning algorithm, that is multiple regression model. Right? If I had to use another machine learning algorithm instead of logistic regression, I would have used multiple regression model. Then I could have used cost saving percentage as my dependent variable. Right? Since I'm using logistic regression, so I'm converting my cost saving percentage into a categorical form, and that categorical form is having binary division. And so we are saying that if any cost saving is more than and equal to 15%, then it is 1. Or if the cost saving percent is less than 15%, then we are going to define this as 0. Right? This is our target variable. So what we are going to define this? This is 1. Right? Now, the logistic regression model has let's say before going to the model, I've also, since we have defined here the dependent variable or target variable or the effect variable, let us define the cost variables. So why these cost savings could go, why the cost savings percentage could go more than and equal to 15%. Similarly, why the cost saving percentage would go less than 15%, right? So we need to know the reasons. What are the reasons? What are the reasons which can impact the cost saving percentage? So those reasons are called the cost variables. So we will name some of the cost variables. We will not build a full-fledged model. We'll build a small model. Right? We keep it very parsimonious. So the cost variables, let's say one is the buyer experience. Cost variable 1. Let's say cost variable 2 is suppliers daily production capacity. Cost variable 3, lead time, distance between this buyer and supplier. Okay, so we're going to take these three cost variables. Then we can build, n number of cost variables. Like, we can build, like if I show you one example which we have worked over here. Look at here, we have n number of variables here: buyer experience, lead time, value of the contract, expiry of the contract days, bulk purchase, contracts, whether exist or not, duration of the contract, sourcing error to RFQ, MOQ, lead deviations, expected margins, cycle count accuracy, failure rate, right? Normalized approval errors. We have taken so many cost variables here. Look at a lot of failure rate, approval error, planning error, ERP efficiency, procurement and inventory integration efficiency, item quality approval rate, item return rate, payments term compliance, right? So we have taken so many of variables, cost variables, to correlate that with the effect variable or the independent variable, right? But we are not going to build such a huge model because this is a small session. So what we're going to do is we're going to restrict our session. So we have to use a small model instead of a big model. Okay, so what I will do is I'll take this transactional data. So we have taken buyer experience. So I'll remove the buyer profile from here. So I'll also remove the so supplier daily production capacity and let's put supplier daily production capacity. So I'm going to create a random data instead of a structured pre distance between supplier and buyer. Okay, so let's say I'm going to use a rand between function. Let me say 10,000. This is for day capacity. 10,000 comma to 40,000. And distance I will use rand between let's say 100 to 1,000. Right, so this is our data we have, and what I'm going to do is I'm going to freeze this data because this right now is a random between. So I'll just copy it and paste special values. So now we have a data over here. So this is our cost variable 1, cost variable 2, cost variable 3. These are the three variables which are going to impact our cost savings percentage. And I'm going to convert this cost saving percentage table into, we have discussed about 15%, right? If anything is more than equal to 15%, we'll say 1. Or anything is less than 15%, then we'll define it 0. So now we have a data which this is our effect variable. These three are the cost variables, right? Now this is our data which we are going to use to actually do the predictions on which scenario, on what are the scenarios on which we are going to make, we have to make a prediction. For prediction, we need a model, mathematical model. So suppose if I have a buyer experience of 3 years or 3.5 years, right? What will happen to my cost saving percentage? If my supplier daily production capacity is 100 units, what is going to happen to my cost savings percentage, right? If the distance between the supplier and buyer is 500 kilometer, what is going to happen to my cost saving percentage, right? What are the chances? So that is what we are going to predict. We need to predict, and for prediction we need to. So before going now, what is we have gone the first layer. The first layer is defining our, the dependent variable, then defining our independent variable. We have done the first step. We build our data, right? We have a data now. That's the second step, right? Now we will go to the concept, or we will go into the logistic regressions algorithm. So going to the algorithm, I just want to explain that logistic regression works on two important concepts. I will say three important concepts. One is the probability, second is odds, and third is the logic. So let us see all these three and how they are correlated. For example, I'll just build a small table, probability of 1, probability of 0, right? And probability of 1 divided by probability of 0. And what is 1? If the cost savings is more than equal to 15%, right? If one is, what is the outcome 1? If it is more than, if the cost savings is more than 15%. What is 0? If the cost savings is less than 15%, right? This is what 1 and 0 means, right? I'm going to build a random distribution of probabilities. So what is probability of 1? Suppose I build a probability here, that is 0.1 to 0.99, sorry, 1 comma 99. I'll divide it by 100. So this is, I'm getting a probability values, and I'm going to build a distribution. And what is probability of 0? That is nothing but 1 minus probability of 1. So what is probability of 1 divided by probability of 0? Just we are going to divide this, right? And this function, probability of 1 divided by probability of 0, is called odds. Okay. Now, what I'm going to do, I'm going to freeze these values, because this is coming from band between, so this will be keep changing. So I want to make them fixed. I'll put a filter here and take a filter, and I'll just sort this data into ascending order. Okay, and then what I will do is I'll build a chart to see the distribution. So I just have to structure the chart now. So I'll remove this particular probability of 1. I'll remove the probability of 0. I'll go to the x-axis and I will select the probability of 1. Okay, so if you look at this chart, the probability of 1 is on the x-axis and the odds is on the y-axis. If you look at this chart, this looks like an exponential distribution. Okay, this chart looks like to have an exponential distribution. Okay, so what I'm going to say that, so my p by 1 minus p by 1 minus p could be defined having an exponential distribution. P by 1 minus P is nothing but a function of whatever is a function. Let's say that function is model. That model is function, right? So this is this is an exponential distribution. Because if you look at this chart, it is exponentially increasing. This is exponentially increasing. So what is the model then? The model is nothing but the log of P1 minus P. The model is nothing but the log of 1 minus P by 1 minus P, because this is an exponential model. So if I remove the exponential, if I do the inverse of the exponential, right, here the exponential will be removed, and here it will take the shape of log. So my predictive model is log of P by 1 minus P. Log of 1 minus P, P by 1 minus P. This is what my predictive model will look like. So if I do the log of P by 1 minus P, log natural of odds, let's see what we get here. If I draw the line, if we draw this, build a plot of this, now this plot is turning into a linear plot. Earlier it was an exponentially distributed plot. Now the exponential distributed plot is turning into a linear plot. Right? So this is an exponential distribution. This is a linear distribution. So in order to convert an exponential distribution into linear distribution, right, we need to take the log of each side. So what we are doing here is log natural P by 1 minus P is equal to log natural of e to the power model. Exponential is whatever is the model we have. So when we take log on each side, what happens is this will remain P of P by 1 minus P, but this will become a pure model. So what is a model? Model is a combination of intercept plus coefficient of cos 1 into cos 1 plus coefficient of cos 2 into cos 2 value plus coefficient of cos 3 into cos 3 value. These are model. So if I put exponential of this is X model, right? So what is that? P by 1 minus P is exponential of this model. And what is log natural P by 1 minus P? That is simply the model. This is the concept behind the logistic regression. So this log natural odds is called logit. Right? This log natural odd is called logit. We're converting an exponential distribution into linear distribution, and generally it is easy to work with a linear distribution. That is the reason why we're converting p by 1 minus p by 1 by p by 1 minus p is equal to log by p by 1 minus p. So p by 1 minus p is called odds. P by 1 minus p is an exponential of a model, because we see this is coming as an exponential distribution. So that's why this is an exponential model distribution. Now we are converting that into a linear model by taking the log of each side. So log by 1 minus p is the okay. So this is the concept behind the logistic regression. So let's build a model now. First of all, we also have to define. I think I have not helped you to define what is probability. So probability is probability of 1, for example. So count of the occurrence. How many times how many times we had a cost savings? More than 15%. The count of occurrence of 1 divided by count of occurrence of 1 plus count of occurrence of 0. Right? This is the probability of 1. And what is the probability of 0? Count of occurrence of 0 divided by count of occurrence of 1 plus count of occurrence of 0. Right? So what we are saying is that suppose we are finding the probability of 0, right? So the count of occurrence of 0 is in the numerator. So whatever is the target of our probability, whatever is the target for which we are finding the probability, that particular occurrence count will be in the numerator, and denominator will be count of occurrence of all the possible outcomes. So we have only two outcomes because we are building a binary case. Either we have probability more than 15%, or more than equal to 15%, or less than equal to 15%. So we have only two outcomes. So there are two possible outcomes. So here we have two possible outcomes, 1 or 0. So in the denominator, we have to add the count of occurrence of all the possible outcomes. This is what probability of 1 and probability of 0. And what is odds? Probability of odds of 1, right? We are saying odds of 1, outcome 1. So that is equal to probability of 1 divided by probability of 0. And what is probability of 0? So probability of 1 divided by 1 minus probability of 1. This is our odds. So we are going to use this structure to build our logistic regression model. These are the important concepts which are being used to build the model. So let's first build our linear regression model. From linear regression, we come up to the So I'll go to data, then I'll go to data analysis, then I'll go to regression. I'll choose my input Y range. So the input Y range is this column. This is our input Y range, and input X range is these are the columns. Okay, we have chosen variables. Do the calculation in the new worksheet. So this is the output. And if you look at the R square is very less, right? This model is too weak, but we'll still build a model for the sake of building a model. But this model is not significant. If we look at, we have to see, look at few things in the model, this particular output for the interpretation of the model. So the R square is 0.03, means it is very weak model. The R square must be, at least 60-70%, more than 60-70%. Okay, if it in some cases it is taken 50% plus, but right now this is 3%. 0.03 means it is a 3%. It's a very weak model, 3.16. And if you look at significance of X, it will be less than 0.05. If you want to have a strong model, means our variables are actually explaining our causes or explaining the variability of the effect or variability of on the effect. Then we say that this particular value is 0.05, means our variables are or causes are explaining the impact or explaining the deviations or variations on the effect in a proper way. That is the meaning of this. Means we have a strong variables or strong causes. So this will be 0.0 less than 0.05 or less than equal to 0.05. But as of now, this is coming 0.68, means it is more than 0.05, and it is very at a very high quantum level. So this is not a very strong model. Now we look at the third aspect is our p-value for the intercept, bias experience, supplier's daily production capacity, distance between supplier and buyer. We look at the p-values here. The p-value should also be less than 0.05, or less than equal to 0.05, because our significance value is 0.05. So if you look at here, the intercept is only having the significance, that is 0.02. But if you look at all other variables like bias experience, negotiation, suppliers, only their production capacity 0.61, 0.51 is for the distance between supplier and buyer. They're not explaining the total effect properly. So we are looking at we're looking now from the individual variable point of view. In the case of ANOVA, we're looking for the collective causes point of view. But in the case of the last table, we're looking from the individual effect, the impact of the cause on the effect. But in the case of ANOVA, we're looking at the combination of all the causes and intercept on the effect. So the combination wise, it is not very strong. Individual causes wise, also it is not very strong. And if you look at the R square, this is also showing 3%. So the causes which we have chosen is not explaining the variance on the effect properly or in a significant way. So if we choose this model, we will have a very poor predictability. If we choose this model, we will have a very poor predictability. So what we need to do is that we need to choose some other variables. We need to choose some other variables, or we may have to do trial and error by eliminating one variable at one time. So we will not do all those things in this particular session because we have very less time to actually build a model. So I'm going to choose this model as it is what I have. So what I will do first is I'll take these coefficients, copy them, and go to the model. And I do the transpose here. Okay, and now I'm going to create my model prediction. First model. So here I'm going to take my intercept is going to be constant. I'll freeze this, right? And then I'll do some product. the sum product of these three comma these three will be constant. You have to fix them. Okay, close the bracket and enter. I'll just make one small changes here. So this is a linear regression model. Okay. So what I am going to do is I am going to convert this linear regression model into exponential regression model, exponential of regression model, because our main model is in an exponential format that we have seen in the last just before. So this I am going to convert into exponential. So this exponential linear regression is called nothing but the odds. If I go back to this one, p by 1 minus p is nothing but exponential of model, right? So what is p by 1 minus p? This is odds. P by 1 minus p is odds. So the model is what? This is the model. Intercept plus coefficient. This is a linear regression model. This is a linear regression model, right? So exponential of linear regression model is nothing but p by 1 minus p, that is odds. So if I say p by 1 minus p is equal to exponential of model, which is a plus bx, okay, then what is p? So p is equal to 1 e to the power 1 e to the power a plus bx into 1 minus p. Okay, so let me remove this equal to sign from here. So we'll keep it p over here same. Here it will become e to the power a plus bx minus e to the power p into e to the power a plus bx. Now what we'll do, P plus P into now we have to find the probability so we find the probability we get a P plus P into e to the a plus bx is equal to e to the power a plus bx so we take the p common here, we get 1 by e plus 1 into a plus bx is equal to e to the power a plus bx. So what is p here? P is equal to e to the power a plus bx divided by 1 plus e to the power a plus bx. Okay, this is the this is p, means p of 1. The probability of 1 is equal to e to the power a plus bx divided by 1 plus e to the power a plus bx. But this is the formula which we are getting for the probability of 1. So this is what we are going to apply in the model. So this is our e to the power a plus n, right? So what we have done, what we have found here is e to the power a plus bx divided by 1 plus e to the power a plus bx. So what I'm going to do here is I'm going to put this as my e to the power a plus bx divided by 1 plus e to the power a plus bx. This is my probability of 1. I know this will take some time to soak in, but if you have any questions, definitely I will be able to answer you. You can WhatsApp me or you can ping me on the social media pages. I'll get back to you. So this is how we are finding the probability of 1 using this particular model, right? But we need to match this 1 with our column C. For example, if this is equal to 0, if this is equal to 1, we'll keep the same value what we have got in the column I. Or if it is not 1, then we are going to subtract this value. So here if you look at, this is 0, right? Actually the historical was 0. So we want to find the model for 0. We have to match, this is history, and we have to match our model with the history. So here we got the probability of 1. For all, this is all for 1. But we have to match this model with our historical model to do the comparison. So if it is 0, then we are going to find the probability for 0, not for 1. So if it is 1, then we are going to find the probability for 1. So if I drag this formula, it will suppose if it is 1, it is 1. It is 0, so 1 minus 0.75, right? This is model map. Let me plot the graph for this. Now what we'll do the optimization. So we'll find the log natural for these values. Okay, and we'll do sum of this values, and what we will do, we'll do the minimization of this sum of this log natural values. For that we'll go into the solver, and our objective is 0.933, and we have to maximize this, and our variables are CD. So this is a model we are getting, and we are saying that the causes are not very strong. This is what we initially also we got. Only this particular intercept is a powerful thing. Rest all causes are not very strong. So this is a model which we have. Suppose if I change the model, if I do some kind of do something. So I'll say or 0.1. So I'm going to make changes here. Look at it, this is almost equal to 0, minus 0.01, this 20 to the power minus 0.6, it's almost equal to 0 only, right? It's not going to make much impact. So that's why it is, if you go to solver and if I do the optimization, I click on solve, right? So this is making all those sort of causes, it is making it almost 0. That is why we're getting 0 over here, and this is 0.68. So this is the model which we have. So if you want to predict, whether what is the probability of 0 means whether so here if you look at the probability of 0 is 0.33%, 33%. So our objective is to predict. Our objective is to predict what will happen if our buyer experience increases or decreases. Now, what will happen if the buyer experience increases or decreases? What will happen if the supplier production capacity increases or decreases? What is going to happen if the distance between supplier and buyer increases or decreases? Right. So, if let's see the first case. Right now, buyer experience is 2 years. Right. If I make it 10 years, what is going to happen here? What is happening? Let's check. If I make my supplier daily production capacity to 200, what is happening here? If I make my distance between supplier and buyer is 200, 2000, what is happening here? So this is almost constant right now because this is 0.68. There is no change. This is only giving the impact of the causes are not having any impact here. So if I put these numbers over here, right now this is not the right way which I am doing. Okay, now let's see. So right now my buyer's experience is 10 years. If I make it 15 years, what happens? The probability of 1 means the cost savings, whether the cost savings is going to is going to more than 15%, is going up 0.436. Suppose if I make it supplier daily production capacity 1000, any impact is there? 0.375. If I increase to 10,000, see the probability of 1 is increasing and probability of 0 is decreasing. So as a supplier, this supplier daily production capacity is increasing, or probability of cost savings is increasing. So we need to choose supplier which has higher daily production capacity in order to improve the probability of cost savings. Suppose if a distance in supplier and buyer, if I reduce to 100, see the probability has increased. The probability of cost savings has increased. Means if I increase the supplier, if I decrease the distance between supplier and buyer, the lead time reduces. The lead time reduces, the cost savings probability increases because it's going to save a lot of money on the fuel. And also, we don't need to order too much at one go. If I supplier negotiation experience increases, that if it is 15 years, I'll make it 20 years. See, let me make 25 years. So, as the negotiation experience increases, here the probability is decreasing. So what I'm going to do is I'm going to try to make this into a ascending order, and let's build one chart between and try to build a chart now. See, as the experience increasing, the probability of cost savings is decreasing. the probability cost saving more than 15% is decreasing. This is for the buyer's experience. Let's see the same thing with the supply daily production capacity. Same thing I will do here. I'll just make the ascending order and build a chart between these two layers. Look at here, as the supplier production capacity is increasing, the probability of cost savings more than 15% is increasing. The effect is not very strong because, as we have already discussed in the beginning, that models are not very strong representative of the effect. Let's try the third one. So here it is decreasing. So as we increase the distance, right? As we increase the distance, the probability of cost savings more than 15% is decreasing. This also makes sense. So if you want to increase our cost savings, we need to decrease the distance between supplier and buyer. We need to increase the daily production. We need to choose suppliers who have more production capacity per day. And the buyer experience in negotiation, we don't need a very high experienced buyer, right? We don't need a very high experienced buyer. We need a medium experienced buyer or energetic, young person who could do much more negotiations, who is more friendly, who is more energetic. It also makes sense. So our model is suggesting, the spend analytics model is suggesting that we need to come up with a buyer who is very energetic and young. We need to choose supplier whose daily production capacity is very high. We need to choose supplier whose distance between supplier and the buyer is very low, right? And we have enough evidence to suggest that yes, if we want to improve our cost savings more than 15%, it means if we have to spend management, right? This is what the model is suggesting to us, and we have used a logistic regression machine learning algorithm to understand the spend analytics, and based upon these suggestions we can do our decision making to generate the spend management solutions. So I've taken a very simple model, and of course these causes are not the strong representation statistically, because the p-values for the entire model is more than 0.05, and the individual variables also p-value is not very significant, right? And also the R square is also not very significant. So this is a very poor model. It's not a strong representation. When we do the real time, we'll not pick these variables for spend analytics solution because they are not the strong representation statistically to generate or to come up with the right evidence to apply to derive the spend management or spend solutions for the company. Okay, so once again I repeat what I have done for the entire. So first of all, we are trying to understand the cause and effect, right? What are the cause? How we define the cause? The cause is not cost savings percentage. The cause is cost savings. We're converting the cost savings percentage into a categorical variable, which is 1 and 0. If it is 1, it is more than 15%, more than equal to 15%. 0, the cost savings is less than 15%, right? We have defined this using a if function. We have categorized it. These are cause, and what these are effects, sorry. And what are the causes? Causes are the buyer's experience in negotiation. Suppose if the experience in the negotiation, the buyer has a longer experience, so can he do better negotiation or not? supplier daily production capacity. If supplier has, daily production capacity is very high, so whether he can give us better cost savings or not. Distance between supplier and buyer. If the distance between supplier and buyer is less or more, based upon what figure or what logic, it is going to give us more cost savings or not. So these are the causes which we have chosen, right? And we have so in the second step we build this data, and third step what we did is we tried to understand what is the model, what is distribution is, right? We understood what is the probability of, what is the formula of probability, what is the formula of odds, right? What is the formula of probability of one. So we have derived all these formulas, and then we saw that if probability of 1 and 0, if we divide both of them and take the log natural of them, what is the distribution is like that. So p by 1 minus p having a exponential distribution, and log natural of p by 1 minus p as a linear distribution. Right? That is the reason why we are converting e to the power a plus bx is equal to 1 by minus 1 p by 1 minus p to the log natural form. Right? Because we want to analyze the linear model, not the exponential model. This is what we are doing over here. So first what we have done is we found a linear model using linear regression method. Then we took the exponential of this linear regression model, which is nothing but odds. Then we found the probability of 1 by dividing e to the power a plus bx by 1 plus e to the power a bx. Then what we did the model mapping, because wherever we 0, we have to compare with the 0. Wherever we have 1, we have to compare with the probability of 1. So wherever is 1, we will take, if it is 0, then we will subtract 1 minus the probability of 1. And wherever it is 1, we will take the same value. Right? It is 0 here, so we are getting 1 minus 0.678. Then we want to do the maximization, so we took the log natural of this model mapping, and then we used the maximization using solver, and then we got the variables, right? And then we are trying to analyze our correlation between the probability and the and effect and the causes. And this is what we have seen here. And then we have a pretty strong understanding about the causes. Of course, these are not the strong causes, but whatever we have chosen, we are getting a strong understanding about the causes. And through this way, we can actually make our strategies and derive the spend solutions, right? So guys, if you want to join our trading programs, you can connect with us on our given email ID, the discretion@mathnal.com, or you can also WhatsApp us at +91 8977 94637, and then we'll take it forward from there. Yes, thank you very much for joining this session, and we'll keep presenting you more and more case studies on supply chain analytics. So please join our pages and groups so that you can get the update on the programs. Thank you very much for joining.